Okay, so this video is going to cover a couple of new elimination products that we maybe haven't seen before, specifically Benzyne and Ketenes. So we're going to start with Benzyne. Um, as soon as I get my pen working. Okay. So Benzyne is an elimination product that comes from benzenes with leaving groups on them. And so if we have a very strong base like sodium amide, we can remove this hydrogen, make a pi bond, kick out a bromine. A pretty standard E2 elimination, except that the weird thing here being that this is all happening on a benzene ring. So benzene itself remains aromatic, it's just that we create a new triple bond at this position. This is our benzyne intermediate. It looks horribly strained because we know that uh, triple bonds tend to prefer 180-degree bond angles. We can't have that here. This is very strained, so therefore very reactive. And it's reactive as an electrophile, right? So we can add a nucleophile to this compound um, at one of these carbons. And so if we add a nucleophile to this, it'll add to that carbon and push these electrons back to that oxygen. And we can get substitution products where the leaving group has left and a nucleophile has been added. And then we would have to figure out what happens with this negative charge here. You could do something like workup or whatever to put a hydrogen there, or other things can occur, right? So more on that in the future. But the main thing here is that if we add a really strong base to a benzene with a leaving group, we can form these benzyne intermediates. Now, nobody really wants to work with sodium amide, and so people have found other less awful ways of generating benzyne. One of those takes advantage of the affinity of fluorine for silicon. And so fluorine and silicon is is strongly favored, right? Fluorine loves silicon. These two things bond together consistently. The fluorine silicon bond is favored, and so when we have F minus, that can add to the silicon. Now, if I really want to get technical here, this is not an SN2 reaction, right? The silicon accepts the fluorine and becomes this pentavalent compound. But what we have here is we have a negative silicon. We have this really great leaving group over here, triflate, a sulfonate leaving group. And so pretty quickly, this silicon can give up its electrons, make the pi bond here, kick out this leaving group, and once again, we generate benzyne. So this is just a milder, right? These are milder conditions, right? KF has its own issues, but in general, KF is easier to handle than sodium amide. And so people prefer, if available, to use this trimethyl group and the triflate group on neighboring carbons, and you can do an elimination once again to make the same benzyne intermediate that we made above, right? A very strained, very reactive, very electrophilic benzyne intermediate. Okay, so if you see these kinds of things, right, leaving groups on benzene rings with strong base around, or this trimethyl and triflate on neighboring carbons like that, this is a hint that benzyne may be something that's formed there. The other kind of new addition, new elimination product that we've talked about as we move through this is when we have a acid chloride and we treat that with an amine base, right? The amine is a base, and so it removes the alpha hydrogen. We get the pretty standard removal of an alpha hydrogen to give us this thing that looks a lot like an enolate, but then instead of reacting as most of our enolate chemistry that we learned in Organic 2 does, when we reform this carbonyl, we instead kick out this leaving group and make a new intermediate, which is a ketene. Right? So it's a ketone and an alkene, it's a ketene. And so now this is once again very reactive, right? There's no steric repulsion around this carbon, and so it's very easy for nucleophiles to add to this. So it's very reactive and very electrophilic. Right? And so we can add a nucleophile to this compound, whether it's a negatively charged nucleophile or a neutral one. And this reacts just like your standard carbonyl in that case, and we generate um, our enolate. Oops. Right, we generate an enolate here, which can then go on and do other reactions. And so once again, the chlorine is kind of replaced by the nucleophile, but we get this elimination reaction where we lose the hydrogen from the alpha position, we lose the chlorine from the carbonyl position, and that generates our double bond here. So you get this elimination followed by addition, and then we can go on and do more enolate chemistry. Right? So it's a way to generate this really reactive compound that has multiple sites of reactivity. We can react at the carbon, and then once again, we can react at the alpha position when we do enolate chemistry. Just like with benzyne, we can react at one of these carbons, right, the electrophilic carbon, and add the nucleophile to one of these two carbons, right, and that generates now a potential nucleophile, and so this can go on and do more reactivity. And so these elimination products in both cases allow us to kind of make things that have multiple sites of reactivity, which from a mechanism standpoint is really exciting because that means that we can kind of do tandem reactions where we do one thing and that leads to another step in our mechanism.